In this video you will learn how to combine the power law, which states that power is the product of voltage and current, with the famous Ohm's law to replace unknown quantities in an equation with known ones. You will also learn under which circumstances a smaller resistance in a circuit leads to either more or less power consumption, depending on several circumstances we will take a look at. And by the end I will show you a simple representation of the most important formulas for power, for resistance, for current and for voltage, which you can use for, let's say, learning for an upcoming exam, or simply remembering the correct equation at the correct point when you are, let's say, designing a circuit. And as always, there's going to be a summary of the most important facts from this video at the end. So stay tuned, and my name is Andreas from The Fearless Engineer, and here we go. Now, before we dive into the new concepts in this video, let's quickly recap some things which we need in order to understand them better, some items from previous videos. And in the video on the power law, we have derived this law from scratch, this very famous concept postulated by James Watt originally, famous English engineer, and he expressed the power P as the function of current I and voltage U. And he arrived at this very simple form here: power P equals voltage times current. And similar to Ohm's law, which states that the voltage is the product of resistance and current, also something which we discussed in a previous video, similar to this law, the unknown variable, or one unknown variable in the power law, can be calculated from two known quantities. Let's make a quick example here. Let's say we have a hairdryer which has a power rating of 1200 watts, and we know that the voltage from the wall socket is at 230 volts. Then we can use the power law, isolate the current I, which we are looking for, and then simply compute the ratio between the power, 1200 watts, and the voltage from the wall socket, 230 volts, and then we arrive at 5.22 amps of current, which are drawn by this particular hairdryer here. So we can use the power law to arrive at unknown variables, and by using known ones in examples such as this one here. Now, one drawback of both laws, both the power law and Ohm's law, is that there are situations in which only one quantity is available for determining the power. That might be either current or power, but not both. And in such cases, we can combine the power law with Ohm's law in the form you can see here at the bottom. We already know the power law, we already know Ohm's law, and if, let's say, we do not have the voltage consumed by a certain electrical device, we can simply plug in Ohm's law, which states that voltage is resistance times current, into the power law, and then we get this very simple form here: power equals resistance times current squared. So we now only need the current measurement and the resistor value, which we might measure using a multimeter, or which we might simply read from, let's say, the color code printed onto the resistor, and then we can compute the power consumption of this resistor. Obviously, this can also be the resistance of a complex device. It doesn't have to be the actual resistor. And in case we want to replace, let's say, the current, because we only have the voltage, we can also use Ohm's law to plug it into the power law equation. We can simply reshape this law here with I on one side and the ratio of U, the voltage and resistance, on the other side. We plug it in here and we arrive at this simple form here. So in the second form, we have power equals voltage squared divided by resistance. And by combining these two, you get a larger number of possibilities which you can use to apply known parameters and arrive at the power usage of a certain electrical device. So the combination of power law and Ohm's law just gives you more possibilities and a higher degree of flexibility. Now let's look at a concrete example. In this example here, reducing the resistance by half leads to a doubling of the power consumption in the load resistor. Let's quickly look at this very simple circuit here. We have an energy source, a voltage source on the left, which has a rating of 2 volts. It's a perfect source, which means the voltage it provides is stable, independent of the load resistor which we connected to. Then we have a current flow of 1 amp and we have a resistor of 2 ohms, which means we can use the power law combined with Ohm's law to use the voltage squared, which is 4 volts squared, divided by the resistance value, and we can then easily compute the power consumption of the resistor, which is at 2 watts in this very simple example. And obviously, if we make the resistor smaller, a larger current is going to flow, which you can see here on the right side. It's now 2 amps, which means that the computation which we can make here regarding the power law in combination with the Ohm's law is also 4 volts squared divided by the new resistance, which is only half the size of the resistor in the left example, and then we get a doubling of the power consumption at 4 watts now, which makes sense because the current has also doubled while the voltage has remained constant. And you should note that this voltage variant of the power law should be used in situations when you can assume that the voltage source is providing a more or less constant voltage independent from the load which you connect it to. When we talk about substitute voltage sources, which also combine an internal resistance value in conjunction with this perfect voltage source, then we will learn that every voltage source, let's say a battery, has an internal resistance which causes a drop in voltage which the voltage source can provide to the circuit. And it all depends on this ratio of internal resistance of the, let's say, battery and the resistance of the circuit which we connect it to. And in such situations, if the voltage source is more or less constant, then you can easily use this variant here of the combination of power law and Ohm's law. But in cases where this is not the case, where the voltage provided by a battery changes significantly depending on the circuit you connect it to, then you might not want to use this form here, but depending on the behavior of the voltage source, you might want to use another form, which we will take a look at on the next slide. In this case here, we have a very similar setup. The only difference is that now we don't have a voltage source, but we have a current source. In this case, it's a perfect current source, which provides 1 amp of current flow through the circuit, which we connected to, independent of the load of the load resistor within the circuit. We also have a 2 ohm resistor here. On the right side, we have halved it. So we have a 1 ohm resistor. R3 is 2 ohms, R4 is 1 ohms. And now, as you can see, when we halve the resistor, the current is not changing. It's 1 amp in both cases, which means that if you apply the other combination of Ohm's law and power law, where we enter the resistance and the current flow, we arrive at a power consumption of 2 watts with a left circuit here. But now, since the resistor has been halved, but the current has remained constant, we get a power consumption of only 1 watt, which is somehow confusing eventually, because on the left side we have double the resistor than on the right side, and usually the expectation is that if you reduce the resistance of a circuit, you increase the current flow, and by this you also increase the power consumption. But with current sources, with constant current sources, it's exactly the opposite case, because if the current remains constant, this means that the voltage drop across the resistor drops, because the voltage drop, according to Ohm's law, is the product of resistance and current. And if the current remains at 1 amp and we halve the resistance value, the voltage drop is also going to be halved. And since power law states that power is the product of voltage and current, it makes sense that in this particular setup here, halving the resistor also halves the power consumption. And this is a situation when you have a current source where you should use this combination of Ohm's law and power law, where you eliminate the voltage, because you can not assume the voltage to be a constant in this setup here, but you can assume that the current is going to stay constant. So opposed to the previous slide where we had a voltage source and used the combination of Ohm's law and power law and let the voltage be constant, now we can assume that the current is going to be constant, which is why we eliminate the voltage. So you always eliminate the variable which is not constant in your particular setup. If you do not know how your circuit will behave, because let's say you are powering it with a solar cell and you do not know that much about the behavior of the solar cell, you might need to take a look at the current voltage characteristic of this cell to make sure that you use the correct forms here, and then you can assume a certain behavior of your power source under the which you build into your circuit, which is powering your circuit. So you always should know about the behavior of the power source which you connect to your circuits. Now let's look at this very useful triangle here. It's called the power triangle. And the idea of this triangle is to help you remember the power law in a very simple way. Let's say you wanted to compute the power from current and voltage, and you are not sure 100% how you can use current and voltage in a correct manner to do so. You can now say that power equals the product of voltage and current. And it's going to be a product because both of them are on the same horizontal level. On the other hand, if you wanted, let's say, to compute the current flow, you can see that the power is above the voltage here, which gives you the hint that you have to use the fraction of power and voltage, and vice versa. If you wanted to compute the voltage, you can easily see from the triangle with power on top that voltage is the fraction, the ratio of power and current on the other hand. It's a rather simple triangle here, but let's say in an exam situation which might be stressful, where you might have forgotten the correct form, this very simple graphical representation of the power law helps you remember the correct equation. Also, this conversion circle here on the right can be used to find the correct form to convert between these values here. In the leftmost corner you have power, and you can easily see all three possibilities which you can use to compute the power, which is the product of voltage and current. And let's say you only have current and resistance, and you can use this form here. Also, if you, for example, wanted to compute the voltage drop and you have power and resistance, you can easily see here that you have to compute the square root of the product of power and resistance. And in this manner, this entire circle can be used in a very convenient manner. This might be something for let's say, a cheat sheet where you collect some equations here. You can easily use this to conduct some exercises related to power and conversion between parameters. Now let's quickly summarize the most important items from this video here. The first is that the power law can be used to calculate missing unknowns from known quantities. You have one unknown and two known quantities in the basic form. And if you combine it with Ohm's law, this power law, then you get other possibilities of parameters which you can use. You can introduce the resistance into the mix of parameters in addition to current and voltage, depending on what's given and also depending on the behavior of the components in your circuit. Which means that the voltage variant of the power law should be used when a constant voltage source is present, and also when the current variant of the power law, the current variant should be used when a constant current source is present, just as in the examples which we have looked at. Now let's quickly summarize the main findings from this video here. We have seen that the power law can be used to calculate a missing quantity from two known quantities very easily, and by combining Ohm's law and the power law we get an even more powerful representation in which we can introduce a third component into the mix, which is the resistance in addition to current and voltage, to compute the power which is consumed in a certain device, let's say in a resistor. And thirdly, the voltage variant of the power law, we have seen two variants of it. The voltage variant of the power law should be used when a constant voltage source is being used in a circuit, let's say a battery. And lastly, the current variant of the power law, this one should be used if a constant current source is present. And a constant current source is a source which does not, or does only to a very small extent, change the current it supplies to a circuit if this circuit changes its resistance. So for current sources, current stays constant. For voltage sources, voltage stays constant. That's all for now. If you have any questions related to this video, don't hesitate to drop me a comment down below in the comment section. Also, if you have any suggestions for future videos which you want me to make, please also leave a comment here. I wish you a nice day now, all the best, and see you next time here on The Fearless Engineer.